Today, we are jumping straight into one of the wildest, most mind-bending ideas in all of physics. It's called the ER equals EPR conjecture. And, it's a story that tries to stitch together two of the absolute strangest concepts in science. If this is right, it could literally change how we think about the fabric of reality itself. So let's get into it. So let's just kick things off with a massive question. What if? What if that thing Einstein famously called spooky action at a distance and the wormholes you see in all the sci-fi movies were actually just two different ways of describing the exact same thing? I know, it sounds pretty out there, but that is the wild idea we are going to unpack right now.
Okay, so to really get our heads around this, we've got to meet the two main characters in this drama. And funnily enough, they both came from the mind of Albert Einstein and his colleagues. But here's the thing. At first glance, you'd think they have absolutely nothing to do with each other. On one side, you've got the ER bridge. That's the Einstein-Rosen bridge. This is basically a wormhole. It's all about geometry, a theoretical tunnel, a shortcut through the very fabric of spacetime. Then in the other corner, you have the EPR paradox. That's Einstein, Podolsky, and Rosen. This is pure quantum weirdness. This is that spooky action we were talking about. You get two particles that are linked, right? And no matter how far apart they get, even across the entire universe, you measure one and the other one instantly knows. So you've got one idea about the shape of space and another about a strange connection that seems to completely ignore space altogether.
And for a long, long time, like for decades, everyone just assumed these were two totally separate ideas. But then physicists started finding these little breadcrumbs, these clues that hinted at something deeper, a real, intimate relationship between them. And it all kicked off when they tried to do something that sounds pretty simple. Just calculate how much entanglement there is in a region of space.
And this is where things get really weird. So physicists have this mathematical tool, and its job is to measure the total amount of entanglement in an area. And it works great for the space itself. But it had this one massive blind spot. If you took two objects that were already entangled with each other and you just dropped them into those regions, the calculation completely failed to see them. It was as if this extra layer of entanglement was totally invisible.
The real aha moment came when they tried this with black holes. So check this out. You have two black holes, they aren't entangled, the math is simple, everything's fine. But the second you entangle them, boom. The equations just break. They don't work. And the only way to make the math work again to account for that invisible entanglement was to assume a new structure had formed between them, a wormhole. The entanglement wasn't just a spooky link. It was literally building a geometric bridge.
So here's the punchline, the really crucial point. Entanglement, that spooky EPR stuff, it isn't just some abstract link. It appears to be the very thing that weaves the geometric connection, the ER bridge. So EPR implies ER. It's a radical idea. Maybe space-time geometry itself is actually built from quantum entanglement.
But, okay, like any great idea in physics, this one immediately creates a big problem, a paradox. We know that in quantum mechanics, if you measure one particle in an entangled pair, the connection breaks. The entanglement is gone. So, what happens to the wormhole, the one that was supposedly made of that entanglement? Does it just poof, vanish? To figure this out, let's play out a little thought experiment. We need some characters, so meet Bob and Charlie. They each have one of a pair of entangled black holes. Now, according to our new ER equals EPR rule, that means there's a wormhole connecting them. So in theory, Bob could jump into his black hole and pop out of Charlie's to say hi. But then, along comes our third observer, Alice.
Alice decides to measure Bob's black hole. Now, from her point of view, it's simple. That measurement she just made broke the entanglement between Bob and Charlie, so the wormhole has to be gone. Her conclusion, Bob and Charlie can't meet anymore. Case closed. But what if we look at this from the outside? Let's bring in a fourth observer, we'll call her Daisy. From her perspective, nothing was destroyed. All that happened was Alice's measuring device got tangled up with the original Bob and Charlie system, so a connection must still exist. So who's right? They can't both be, can they?
The resolution to this puzzle is just, it's beautiful. It's strange, but it's incredibly elegant, and it forces us to think about a more complex kind of connection, not a simple two-way street, but more like a three-way quantum intersection. And the key that unlocks the whole thing is a special kind of link called GHZ entanglement. It's named after the physicists who figured it out, Greenberger, Horn, and Zillinger. Now, this isn't your standard two-way connection. It's a strange collective entanglement that joins three or more partners together in a very, very specific way. So before Alice shows up, the situation is simple. You can think of this diagram as basically a map of the connection. You can see a clean two-way wormhole linking Bob's black hole and Charlie's. Easy enough. But now, watch what happens after Alice's measurement. The wormhole doesn't vanish. It morphs. The original two-way bridge transforms into this bizarre new three-way junction, a GHZ core that now connects Alice, Bob, and Charlie all together. And this is how the paradox just dissolves. This GHZ state has very specific properties. If you look at just two of them, Bob and Charlie, they are no longer entangled. They can't meet. Alice was right. But, and this is the amazing part, if you look at any one of them, they are still maximally entangled with the other two combined. A deep connection still exists. So Daisy was also right. Everyone's perspective was correct. It's brilliant. Okay, so if entanglement is the fabric of wormholes, can we actually use it? The theory suggests yes. This whole thing reframes entanglement, not just as a weird fact of nature, but as a real physical resource. One of the pioneers of this idea, Leonard Susskind, puts it perfectly. He says entanglement is a fungible resource. Now, fungible just means you can convert one form into another, kind of like how you can convert chemical energy from a battery into electrical energy. Well, he argues you should be able to do the same with entanglement, like turning the entanglement between a bunch of particles into a full-blown wormhole. And this opens the door to a geometric way of looking at quantum teleportation. Imagine Charlie wants to send a complex quantum state, what physicists lovingly call his big bag of complexity, over to Bob. First, he fuses that state with his end of their shared wormhole. Then, with a simple measurement, he snips his end off. Instantly, the complexity appears on Bob's side. All that's left for Charlie to send a quick classical message, like an email, telling Bob how to unscramble it. Now, here is the truly astonishing part. A quantum state can be exponentially complex. I mean, it can contain a vast, vast amount of information, but it can be teleported using a classical message that is just tiny in comparison. It's an incredibly efficient transfer of information, all visualized as passing a message right through a wormhole. Ultimately, what all of this points to is a conclusion so profound it could rewrite textbooks. As the researchers put it, maybe, just maybe, geometry and quantum mechanics are so inseparably joined that each may not make sense without the other. They aren't two different subjects. They're one and the same. Which leaves us with a final, tantalizing thought to chew on. If the very space we live in is woven from these invisible threads of quantum entanglement, what else about our reality is just hiding in plain sight, waiting to be rediscovered?